Hi, I'm Quinn, and today we're unpacking quantum key distribution. Every time you send a message online, your credit card number, your password, your private photos, you're trusting mathematics to keep it safe. Specifically, you're trusting that certain math problems are really hard to solve. Like factoring huge numbers. Sure, in theory someone could factor the number protecting your bank account. But it would take thousands of years with today's computers, so you're probably fine. Probably. But here's the thing about really hard math problems. They're only hard until they're not. Maybe someone invents a better algorithm. Maybe quantum computers get good enough to break it. Maybe there's a backdoor nobody noticed. The security isn't based on physical law. It's based on hope. Hope that nobody's smarter than we think. And that's made cryptographers nervous for decades. So here's the question. Can we do better? Can we create encryption that isn't based on hard math problems, but on something more fundamental? Something unbreakable, not because we think it's hard, but because the universe itself says it's impossible? The answer is yes. And it's called quantum key distribution. First, let me explain the basic problem. When you want to send me a secret message, we need to agree on a key, basically a password that we both know but nobody else does. Once we share that key, encrypting messages is easy. The hard part, sharing the key in the first place without anyone intercepting it. Traditionally, we solve this with math. We use algorithms where I can send you information publicly, you can send me information publicly, and somehow, through mathematical magic, we end up with a shared secret that nobody eavesdropping could figure out. That's how your browser talks to your bank. But again, it's all based on mathematical difficulty, not impossibility. Quantum key distribution takes a completely different approach. Instead of relying on hard math, it exploits the fundamental laws of physics, specifically two quantum rules. 1. You cannot copy an unknown quantum state. This is called the no-cloning theorem. If you don't already know what state a quantum particle is in, you cannot make a perfect duplicate of it. Period. The universe forbids it. 2. Measuring a quantum system disturbs it. When you observe a quantum particle, you fundamentally change it. There's no such thing as just peeking. Here's how it works in practice. Let's say I want to send you a secret key. I start sending you photons, particles of light. But these aren't ordinary photons. Each one is polarized in a specific direction. Think of it like the photon is vibrating in a particular orientation: vertical, horizontal, diagonal, or anti-diagonal. I randomly choose which direction for each photon. Vertical might represent a 0. Horizontal might represent a 1. I'm building a string of random bits. 0, 1, 1, 0, 1. You receive the photons and measure them. But here's the catch. You have to choose how to measure each one. You can measure in the vertical/horizontal basis, or the diagonal/anti-diagonal basis. You pick randomly. Sometimes you'll measure in the right basis, the same one I used to encode that photon. When that happens, you get the right answer. But sometimes you'll measure in the wrong basis and you'll get, well, a random result that's useless. So after I've sent you, say, 1,000 photons, we get on a regular phone call. Anyone can listen, we don't care, and we compare notes. Not the actual results, just which basis each of us used for each photon. First photon, I used vertical/horizontal. Me too. Great, keep that one. Second photon, I used diagonal. I used vertical/horizontal, darn. Okay, throw that one out. We go through the whole list. We discard about half the photons where we used different bases. The ones where we matched. We both got the same result. That's our key. Now here's where it gets beautiful. What if someone, let's call her Eve, tries to eavesdrop? Eve intercepts the photons between me and you. She wants to measure them to see what the key is, then send them on to you so we don't notice. But remember rule number 2. Measuring disturbs the quantum state. When Eve measures a photon, she has to guess which basis to use. Just like you did. If she guesses wrong, which she will about half the time, she doesn't just get the wrong answer. She destroys the original state. Then she has to send something to you. But she can't send the original photon, she destroyed it. She has to send a new photon based on her measurement. Which means it's in the wrong state about half the time. So how do we catch her? After we've compared bases and built our key, we do one more thing. We sacrifice a random portion of our key, maybe 10%, and compare the actual results publicly. Third photon, where we both used vertical/horizontal, I got 0. I got 0 too. 11th photon where we both used diagonal. I got one. I got one. If nobody was eavesdropping, we should match 100%. Every single time. But if Eve was eavesdropping, she introduced errors. Random errors from her wrong basis measurements. If we see even a small percentage of mismatches, boom, we know someone was listening. We throw out the entire key and start over. The eavesdropper can't avoid this. It's not a question of being clever or having better technology. The laws of quantum mechanics guarantee that any attempt to intercept and measure the photons will leave detectable errors. Do you see what just happened? We went from security based on, this math problem is probably too hard for you, to security based on, the fundamental laws of physics make this impossible. It's not cryptography anymore. It's physics. If the key is compromised, we know before we send a single bit of actual data. The intercepted key becomes useless before it's ever used. Now, to be fair, quantum key distribution isn't perfect for everything. You need a direct connection, usually a fiber optic cable, between you and the person you're talking to. You can't easily route it through the internet. The distances are limited. The equipment is expensive. But for high-security applications, government communications, financial institutions, critical infrastructure, it's already being deployed. There are QKD networks running in China, Europe, and the United States right now. Here are final takeaways. First, traditional encryption relies on hard math problems, things that are difficult but not impossible to break. Quantum key distribution shifts security from mathematical complexity to physical law. Second, the no-cloning theorem and measurement disturbance aren't bugs, they're features. Any eavesdropper trying to intercept quantum keys will inevitably leave detectable errors in the signal. Third, detection happens before any sensitive data is sent. If someone's listening, you know immediately and can discard the compromised key. The intercepted key becomes useless before it's ever used. Fourth, this isn't theoretical security, it's absolute. You're not betting that hackers aren't smart enough or computers aren't fast enough. You're relying on the fundamental laws of physics that govern our universe. Fifth, QKD isn't perfect for everything yet. It requires direct connections and specialized equipment. But for high-security applications, it's already being deployed in real-world networks around the globe. Sixth, for the first time in history, we have encryption that isn't based on assumptions. Not on computational complexity. Not on secrets. Just on the universe itself saying, you cannot observe without disturbing. You cannot copy without knowing. And if you try, you will leave a trace. That's not just unbreakable encryption. That's physics telling eavesdroppers, not today. And that's genuinely revolutionary. That's all for today. Take care.